inverse functions, which we have seen earlier in the year. So let's recap. We know that if there is a one-to-one relationship between two sets of numbers, then both the relation and the inverse relation become functions. So in other words, it satisfies both the horizontal line test, but it would also satisfy a vertical line test. So it satisfies both. So in that case, instead of calling it an inverse relation, we call it the inverse function. I suppose another way of saying that is, if the inverse relation turns out to be a function, then we call it an inverse function. Okay, so we know a function is either one-to-one or many-to-one. Okay, so if the function is one-to-one, then we know the composite of the function and its inverse will always be x. So if you sub a function into its inverse, you get x. Or if you sub the inverse into the function, you get x. So if you want to test for inverse functions, that's the easiest way is a horizontal line test. So you know it's a function because it satisfied the vertical line test. You look at the picture, oh look, it also satisfies a horizontal line test. Therefore we know we'll have an inverse function rather than an inverse relation. And the other way then is to rearrange it, so swap the x and the y around, and you'll end up with x equals function y, but make y the subject of that, and you end up with something that is unique. So you don't find yourself saying something like plus or minus the square root. So plus or minus wouldn't be unique. You've got two possibilities. Now, an inverse function of an odd function will always be odd, and even functions won't have inverse functions, because it will always fail the horizontal line test, because that even function, remember, will have symmetry in the y-axis. Domain and range. Okay, so we know AB is a point on the original function. Again, the y's and the x's swap round. So BA will become a point on the inverse. And so that's another way of working out domain and range. Sometimes you might find, rather than trying to find the range is the one most people have issues with, rather than trying to find the range of a function, try and find the domain of its inverse, because they should swap around. The domain of the function will be the range of the inverse, and the range of the function will be the domain of the inverse. So let's have a look at a couple of, well, very simple examples. Our basic exponential curve, y equals e to the power of x. Now we know the domain of that's all real x, and the range is y is greater than 0. The inverse, well, if we swap the x and the y around, we get x equals e to the power of y. But if I want to make y the subject, then we use logs. So y would equal the log of x. In this case, it would be the natural log, because it would have to be base e. That base is not going to change. And the domain of a log curve, you remember, is x is greater than 0, but the range is all real y. So again, we can see that the domain and the range have swapped around. And if we were to draw it, they would be reflections in the line y equals x. And so I've just dotted in a y equals x there, and so the log curve looks something like that. Nice and symmetry there. The reality is, most things don't have an inverse function because of failing that horizontal line test. So unless a curve is continually increasing or continually decreasing, it's always going to come back on itself and it won't satisfy a horizontal line test. So we need to restrict domains. If we want to look at inverses, we usually have to restrict the domain of the original function so that it will satisfy a horizontal line test. So we can make it invertible, and then the inverse function will become one-to-one, or the original function, I should say, will become one-to-one. So you choose the domain. There are different domains you could pick. So as an idea, then you want to get the piece. Remember I said we want it to be continually increasing or continually decreasing. So you look at the graph and you say, right, I want to grab a piece of this which is always increasing and always decreasing. So let's have a look at y equals x squared. So our basic parabola. Now clearly fails the horizontal line test. Its domain's all real x, range is y is greater than or equal to 0, but nope, won't have an inverse. So we want to choose a piece of that parabola which is continually increasing or continually decreasing. So we've got two choices. We usually go with the positives rather than the negatives. So you don't have to, But the standard way, I guess, of doing it is we'll go with the positives. So the piece I'm going to pick, so it's continually increasing, is x is greater than or equal to 0. And 0 is the other point we try to include if we can. The range of that is still y is greater than 0. So we would like to, if we can, keep the complete range as well. So we were able to do that. We got a piece of the curve, we keep all the range intact, and what would the inverse be? Well, we get x equals y squared, so y becomes x to the power of a half. Now it's not plus or minus because of our restriction. So the domain is now x is greater than 0, and the range of that is y is greater than 0 for the inverse function. And the reflection, there's y equals x. Essentially we end up with the top half of the parabola. Now, had I restricted it such that it was x is less than or equal to 0, then the inverse would have become the minus the square root of x. I would have ended up with the bottom half of that sideways parabola. All right, let's have a look at an old HSC question there. So we have function x equals e to the minus x squared, a bit of a bell-shaped curve, they call those, that have that type of shape. They've told us the graph has 2 points of inflection, so where it changes concavity. Find the x coordinates of those points. Now we know possible inflection points will occur when the second derivative is equal to 0. Now that comes down to concavity. Second derivative measures concavity. So if the second derivative is 0, we're saying it has no concavity. Well, if it has no concavity, that's where it must change. It's like when you're moving forward and you want to go backwards. Well, before you can do that, you've got to stop. And so it's the same sort of idea. Before I can change from concave up to concave down, I've got to stop the concavity, have a concavity of 0. So let's solve that. Well, the first derivative would be minus 2x e to the minus x squared. Differentiate it again, and we have to go use a product rule on that one. Write down the first if the second plus write down the second if the first. And we want that to equal 0. Now, e to the minus x squared equals 0. But anyway, that can't equal 0.
Yeah, it can't equal 0.
Yeah. So therefore it must be 4x squared minus 2 is equal to 0, which gives us two possibilities, plus or minus 1 on root 2. Now, normally we'd go and test to see if they definitely are, because you see how I've got possible inflection points. But because they've told me there's 2, and I've only come up with 2 possibilities, I don't need to test. Because they told me there was 2, and I found only 2, they got to be inflection points there. So the next part of this question in the HSC was explain why the domain of the function must be restricted if function x is to have an inverse. And that's all to do with it has a one-to-one relationship. So basically they're looking that you know the definition or the condition for it to have an inverse. So you want to say it fails a horizontal line test, or it's a one-to-one function, that sort of thing. Part C, well, now go and find the inverse. So all right, we swap the x and the y's around. So x equals e to the minus y squared. I want to make y the subject, so let's log both sides. So we get our log x. So y squared is minus log x, and you might be looking at that and thinking, hang on a sec, y squared can't be minus, but that's all right because log x doesn't have to be positive. Log x can be negative. So y will equal log of x to the minus 1 is 1 on x, of course. So y squared is 1 on x. Y squared then is plus or minus. Now we have to take into account our restriction to see which one it was. Well, again, if you look at the original curve, I want to grab a piece of that curve so that it's continually increasing or decreasing. In this case, I'm going to grab the piece that's continually decreasing, so that way I'll get the positives, I'll get 0 as well. And so we'll have y is greater than or equal to 0. So our eventual function becomes y equals the square root of the log of 1 on x. So now we're going to have a look at what is the domain. Well, the domain of the inverse would be the range of the original function. And the original function was going from 0 to 1. So therefore that becomes the domain of the inverse function. And then sketch the curve. So we want to sketch this and we'd reflect it in, yeah, let's just like that. I've amazingly been able to do a very accurate one. Computers are wonderful, aren't they? All right, so 17A, we'll have a bit of a recap on our inverse functions.